right, well, Cynthia's talk was the perfect segue into my talk. She ended with adaptation, and that's right where I'm going to pick up on. So it's almost like we planned it. We didn't. All right. So, as we just heard, we've had tremendous effort going into trying to improve our estimation of climate impacts. This is not from my work, but this is a paper that was a couple years ago in PNAS, including a lot of AgMIP authors and models. And you can see convergence in impacts among estimates among different methodologies here. But there's still substantial uncertainties and substantial unquantified uncertainties because these sorts of analyses tend to assume that crop area distributions stay the same in the future, that the cultivars that we're using stay the same, that planting and harvest dates stay the same, and other agronomic practices. But if we know anything about the history of agriculture, it's that agriculture is constantly changing, right? So it begs this question of adaptation, of how can we adapt to climate change? How much can we adapt? And I think this emerging field of climate adaptation in agriculture requires not only the scenario analyses, which I think probably predominate, but also retrospective studies that look back and ask, how much adaptation can we see occurring in the past, and what does that tell us about the future? So IPCC defines adaptation as adjustment to actual or expected climate and its effects. So, we're usually thinking about negative changes, so we're trying to moderate or avoid harm, but in the case that there's a beneficial change, we're also thinking about adaptation as exploiting that beneficial change. So I find it helpful to think about adaptation in a few big groupings. So number one is in situ adaptation. What are we doing with a particular crop in a particular location, like changing planting times or switching cultivars? Zooming out a little bit, we can think about adaptation through migration of crops across the landscape. And that would be the collective result of a bunch of individual decisions in response to market forces surrounding impacting crop choice or decisions about rotations or diversification. And then lastly, what Cynthia was kind of just alluding to, the changes in infrastructure and the support system surrounding agriculture, whether that's around crop breeding or also water management systems and irrigation. All right, so I want to just hit upon some examples from my work that touch upon each of these categories of adaptation. And I want to start by looking at U.S. dairy systems. So what we did is we looked historically at dairy yields and their exposure to temperature and humidity stress. That's represented here in this THI index, basically like a heat stress index. And really clearly you can see pop out the negative yield response to cold stress and to heat stress. But what's really interesting is when you break this up and look at this effect over time, the more recent years are much less sensitive overall to weather variations than they were in the past. So you can see that with this red line of the latter 2 decades of the time series versus the first 2 decades. And interestingly, there's also spatial adaptation that pops out with cold places are more adapted to cold and hot places more adapted to heat. So if we look since the 80s, what the combined effect is of climate change and this adaptation effect through decreased weather sensitivity, overall there's a pretty large benefit, around 4.5%. And that's really hardly any of that is due to historical climate change. This is pretty much all due to the adaptation effect of just decreasing the overall sensitivity to weather And we think that has a lot to do with changes in infrastructure like misters, shading, fans, and barns. All right, another system where we've seen in situ adaptation is U.S. maize. So since the 80s, planting begins around 10 days earlier, and the grain filling period of crop development, when the plant is packing on biomass to the grain, is about 1 week longer. And in the U.S. Corn Belt, we've also had this kind of surprisingly benevolent climate trends with decreased extremely hot summer temperatures. So what we wanted to do to look at adaptation is to take this new phenology that's emerged in terms of earlier planting and longer grain filling period, and then we modeled the effect of that new phenology using the weather of every year. And you can see that it leads to an overall yield benefit, and that there's actually a slight trend in that where the new phenology is a little bit more helpful in the weather of the recent years. Now I want to talk about adaptation through migration. So migration of natural systems in response to climate change has been really a major topic of ecological literature, but it hasn't been explored quite as much in agricultural systems. So we sought to correct that by looking retrospectively at trends in rain-fed crop areas over time. Here's from the 1970s to up through 2012. And we can see where these crops have expanded and contracted. And you can see, for example, in this region of the US, we've had an overall shift in rain-fed maize production up to more of the northern Great Plains. So we want to know, does this crop migration influence climate change exposure? Are we moving away from the hottest locations? And the answer for maize is yes. So this is looking at average growing season temperatures and the 95th percentile of those growing season temperatures. The gray line is the trend that we would have seen if crop areas stayed where they were in the 70s. But the red line is the climate change that we actually experienced, given that crops are moving around. And it's about 40% less of a trend. So it's definitely still warming substantially, but it is less than we would have seen otherwise. And we saw similar trends for the other rain-fed cereals. Soybean is, of course, an interesting contrast because it's gone crazy in hot locations. And so for soybean, the red line is above the gray line by quite a bit. All right, and then lastly, I want to hit upon this idea of kind of infrastructure adaptation and focus on irrigation and snowmelt. This is showing the San Joaquin Basin in California. These are surface water demands in the bars and surface water supplies in the lines coming from rainfall runoff and snowmelt runoff. And you can see the crucial service that snowmelt provides in this region by extending surface water supplies into the growing season, but also how that's expected to dramatically change in the future with changes in timing and magnitude of the snowmelt. And that means that we're relying on alternatives for more of the growing season, so reservoir storage and interbasin transfers. These are all the places around the world where we show are at high risk to changes in snowmelt, and it allows us to start thinking about adaptation priorities for these different basins and what's going on. So just for example, in Amu Darya, those alternative water demands under the 4C scenario reach over 70% of available reservoir capacity. So it's really stressing the existing capacity. So we have to think about, how is reservoir management going to change? Where are shifts to groundwater possible? Where are they not? Or crop switching and dryland farming. And so with that, I'll wrap up. I think hopefully we're all in agreement that adaptation is really critical to determining climate impacts. I think it's helpful to think about these different categories of adaptation and to also think about what we can learn from retrospective studies. So thanks so much.